The model of a congestion game is composed of some elements. At first, we have users that are the players. Then we have resources. Every user can use the resources. The specific subset of resources a user can use depends on the actions she chooses. An action is a subset of resources. For instance, an action can include the first and the third resources, or the third and the fifth resources, or the fourth and the fifth resources, and so on. The actions may include a different number of resources, and every player may have a different space of actions. The next element of the model is the congestion. Every resource is congested by the players. More specifically, the congestion of a resource is equal to the number of players that use that resource. Then, using a resource has a cost that depends on the congestion. In practice, we have a function that, given the congestion of the resource, returns the cost. Since the congestion may assume, usually, a finite set of discrete values, the cost function can be represented as a vector, where in the first position we have the cost when the congestion is 1, and so on. Finally, every user incurs a cost given by the sum of the cost of the resources she uses. Consider this simple example. Assume for simplicity that every player has the same space of actions and every action is just a single resource. Suppose that the users choose the resources as in the picture. So the first player uses resource 1, the second user uses resource 2, and so on. Here we have the congestion of each resource. It is 1 for the first 3 resources, 2 for resource 4 and 3, for resource 5. Finally, we have the cost associated with these resources that, in this case, are the same cost of the users, given that the actions are single resources. So the first users incurs a cost of 2, the second user incurs a cost of 0, and so on. That is the cost in blue in the figure. Here an example of a congestion game describing a routing problem in a simple network. The node A is the source, while the node B is the sink. The resources are the edges. Notice that in this case, the edges are direct. An action is a subset of resources connecting the source to the sink. Thus, we have 3 actions. The first action is given by resources 1 and 4. The second action is given by resources 1, 3, and 5. The third action is given by resources 2 and 5. In congestion games, a special function called potential function can be defined. This function is denoted by the letter phi and associate each action profile with a number. The number is defined as a double sum. The first sum is over all the resources from 1 to m, that is the number of the resources. The second sum is from 1 to the congestion of resources j. The term that we must sum is the cost of resource j at congestion k. In other words, the potential function is given by the sum for every resource of the cost of that resource for all the values of the congestion from 1 to the actual congestion. Consider this example. For simplicity, assume that all the actions include only one resource. So we have one player selecting resource 1, one player selecting resource 2, one player selecting resource 3, two players selecting resource 4, and three players selecting resource 5. Thus, the potential function is given by summing all the costs in blue in the slide. That is, 2 for resource 1, corresponding to only one level of congestion, 0 for resource 2, 1 for resource 3, 2 and 3 for resource 4, and 3 times 1 for resource 5. The total value is 11. Suppose to compute the variation of the potential function when a player switches. Suppose that the player selecting resource 3 switches. This means that the potential function will reduce by 1, that is the cost in selecting the resource 3. And suppose that the previous player switches to resource 2. Thus, the potential function will increase by 2. The total variation is therefore 1. Interesting, the variation of potential function phi is equal to the variation of the cost incurred to the switching player. Indeed, the player incurs initially a cost of 1, and after the switch, a cost of 2. So the variation of the cost for that player is exactly 1. That is the variation of the potential function. This equivalence between the variation of the potential function and the cost of the switching player holds in every congestion game, independently of the definition of the space of the actions. So it is a property of every congestion game. We can exploit this property to prove an important theorem. That is, every congestion game always admits at least a pure strategy Nash equilibrium. The proof is based on a simple algorithm. Given an action profile, we select a player that is not playing her best response. Notice that if every player is playing her best response, we have a pure strategy Nash equilibrium by definition. Then, we make that this player plays her best response. This corresponds to a switch. And the switch leads to a reduction of the potential function by a finite value, because the difference for the utility of the player is equal to the difference in the potential function. So if the player is reducing the cost, also the potential function will reduce the value. Repeat it until a pure Nash equilibrium is not reached. Thus, the potential function repeatedly reduces at each step, since the potential function is lower bounded and at each step the potential function is reduced by a non-infinitesimal value, the algorithm must terminate, and the termination can be only at pure strategy Nash equilibrium. The previous proof shows that path in which at each step a single player plays a best response lead to a pure strategy Nash equilibrium in finite time. This holds for every path in congestion game. This property is important in practice, since every congestion game can be solved sequentially by the players just by observing their current cost and the cost they will incur if they switch. In other words, the players can reach a Nash equilibrium just considering their own cost. We provide an example of best response path. Consider the example in the slide in which all the actions include a single resource. Consider the first player. The cost she perceives is 2. She can reduce the cost by switching to resource 3. Here the switch. Consider the next player. The cost is 2. She cannot reduce the cost since resource 1 will require a cost of 2. Resource 3 will require a cost of 5. Resource 4 a cost of 4. Resource 5 a cost of 8. The same holds for the next player. The same holds for the next player. Consider this player. The cost she perceives is 3. The best response of this player is resource 1, requiring a cost of 2. Here the switch. Consider this player. The cost now is 2. The player cannot strictly reduce the cost. Consider this player. The cost is 6. The best response of this player is resource 2. Here the switch. Consider this player. The cost is 4. The best response of this player is resource 4. Here the switch. Consider this player. She cannot strictly reduce the cost. And the same happens with all the other players. Thus, we found a Nash equilibrium. Notice that if the game admits multiple Nash equilibria, different best response paths may lead to different Nash equilibria. One could question whether the property that the best response path leads a pure Nash equilibrium holds only in congestion games or in every generic game admitting a pure Nash equilibrium. This is not true. In a generic game, even with 2 players, a best response path may not lead to any pure strategy Nash equilibrium, even if it exists. The outcome marked in red is a Nash equilibrium in pure strategies. Now consider the following best response path, starting from the outcome marked in orange. Player 2 will play her best response in this way. Then player 1 will play her best response, reaching this outcome. Then player 2 will play her best response, reaching this outcome. And finally, player 1 will play her best response, reaching this outcome. So these best response dynamics enter an infinite loop. Furthermore, one could question whether a best response dynamics in which multiple players switch lead to a pure strategy Nash equilibrium. Consider this simple game in which every best response dynamics with a single switch per step leads to a pure Nash equilibrium. That is, any outcome with payoff 2-2. Consider now the case in which multiple players may switch simultaneously. Here the result. Starting from any outcome with payoff 1-1, if both players switch simultaneously, they reach another outcome 1-1. So the players repeatedly switch from an outcome 1-1 to another outcome 1-1. Thus, any best response dynamics in which multiple players switch simultaneously have no guarantee to converge to a pure strategy Nash equilibrium. Now, we pose an interesting question. How long are the best response paths? Obviously, we are interested in the worst case, that is, in the longest dynamics. The length depends on the number of resources, on the number of players, but more importantly, on the number of resources included in every action. We focus on the most simple case. That is, in congestion games, where every action includes only one resource. These games are called singleton. At first, we can show that given a congestion game with n players and m resources, we can always produce an equivalent game in which the costs are upper bounded by n multiplied by m. With equivalence, we mean that the space of the pure strategy Nash equilibria is the same. The intuition here is that we can change the cost of the resources, preserving the preferences of the players over the use of the resources. Here an example. With 5 resources and 4 players. The costs are those reported in the slide. We report in blue the modified cost, preserving the equivalence. In the modified cost, we have that the values can be in the range 1 to m multiplied by m. That is, in this case, 4 multiplied by 5. At first, we focus on the smallest cost. It is 0 in yellow. In the modified cost, we report 1. Then we have a cost of 1 in yellow, and we report 2 in the modified cost. Then we have a cost of 2, and we report 3 in the modified cost. Next, we have a cost of 3, and we report 4 in the modified cost. Now we have a cost of 4, and we report 5 in the modified cost. And so on, obtaining the modified cost reported in the slide. In the worst case, all the original costs are different, leading to n multiplied by m different new costs in the range from 1 to n multiplied by m. Now we can bound the best response dynamics in singleton congestion games. We know that the costs are upper bounded by n multiplied by m. We know by construction that at each switch due to a best response, the potential function reduces by at least 1. So if we upper bound the potential function, we upper bound the length of the dynamics, given that the potential function has always non-negative values. This is the definition of the potential function. Now we substitute the cost of the resource in function of the congestion with the upper bound, that is n multiplied by m. So we obtain an obvious upper bound to the maximum value of the potential function. Next, we have two sums, one over the resources and another over the congestion of each resource. A coarse upper bound could be that of multiplying by the number of players, given that the congestion cannot be larger than the number of players, and by the number of resources. However, we can do better. Since we have n players, we have that the sum over the congestion of all the resources is exactly the number of players, that is n. So we obtain the upper bound in the slide. The length of the dynamics rises exponentially in the number of resources included in the action. When the number of resources in the action is free, the problem is NP-hard.